This clip is about doing some vector graphics in spatial context XYZ coordinate system, and we use the VPython library, which is a very tight little wrapper around OpenGL that doesn't require a huge amount of time and energy investment to start getting some fun results. What I'm showing here is a pattern that works for lots of students as well as faculty, which is just bare HTML and a portfolio of papers that you've authored with source code and stuff like that, a very open academic flavor. With, in my case, Python is what I have mostly right now as far as source code, but you can imagine different kinds of stashes, different kinds of, you'll find these kind of sites all over the internet. What I'm doing is accessing my own site here, and I hear my dog in the background, so this is very local here, and I'm downloading to my hard drive. I think the server might be in Texas, I don't know. I've lost track. But what I'm doing here is I'm pulling up something I just saved to do some computer graphics, and I'm going to talk you through the source code a little bit with the understanding that you may not care all that much about the details here because you're writing your own vector class. It's not hard to dash one out, debug it, and use it. And what I'm doing, though, in particular here, is wrapping the VPython vector. I'm using its internal capabilities as part of my own class's capabilities, but I'm not subclassing it. It's more of a kind of a composition here, where I'm wrapping it, is actually what they say is design pattern here. And for example, I don't want to, just because I instantiate a vector, I don't necessarily want to have it created on the screen. I want an explicit draw method, and I want this to invoke VPython cylinder class, or sorry, cylinder object. So what I'm doing here is explicitly making the draw be a method. And so when I create axes and plot functions, which are the two other utilities provided here, it's by using this particular line of code where the cylinder in VPython is anchored always to the origin. You see that 0, 0, 0. My vectors are tail originating at the origin. And so when I want an edge, what I need is to use my other main class in there, my edge class. And the two tips of the vectors constitute my edge, so I can connect any 2 points that way, get my polyhedras and so forth. Well, let's see. So at the bottom of modules, I always encourage students to look for tests. That's a style of writing a module that I encourage authors to do. Test your module at the end with code, and so people can see kind of what the code can do. And you can see if you've broken it when you've made some changes. You've got your handy-dandy tests. Give it a workout. It's like stretching before or after exercise, your main exercise. So the first test, it's a little hard to see actually, the black background, especially low resolution. I don't know what resolution you're watching this on, but at low res, okay, that's better a little, but it's a sine wave, cosine wave. So apparently test me is some simple plot of some kind of sine wave, it looks like. Okay, well, we'll look at the source code, but provided we trust the source code, it's okay to run the tests first. Now, the issues of trust are large, and I'm not going to go into them for that reason in this little video clip. My second test, we have what look to be parabolas or polynomials, and we're going to confirm that in a second. I'm going to take you behind the scenes to where we actually, the puppet theater has its sort of backstage, and where all the strings get pulled basically is here we are. And Snaky Wakey, kind of an idiosyncratic name there, is a polynomial to some degree, and then we have this ability to take its derivative in a kind of discrete way, approximate derivative obviously, and we even take the second derivative, and then we plot these guys. So that's why you saw those different curves. You're basically just exploring differential calculus a little bit. So how do we get a domain for a function? I have this built-in dgen And instead of trying to use range or some of these built-ins, just create an arbitrary start and step and go forward with that as your kind of domain generator. And then feed your domain and your function to a plotter. So that's the design pattern here, is that the plotter basically expects a source of data, so D for data or D for domain, and then a function to work on that data. And what it creates is then a generator also. And as you next through the graph, through the plotter, you'll get your graph, to as many points as you care to see. So then we have various, we show that a few times. Let's see yeah. So once you're good at this, you can, sky's the limit as to what you can use Stickworks for. And I don't think there's any doubt that Python is going to accelerate our teaching of computer graphics in the lower grades.